In 1964, astronomers discovered a strange source of X-rays, and it turned out to be the first black hole ever found, Cygnus X-1. Decades later, it's still rewriting what we know about gravity, matter, and time itself. If you enjoy exploring the mysteries of the universe, please subscribe and share, and tell us in the comments, what do you think lies beyond the edge of a black hole? Thank you for watching. Now let's begin. The Milky Way extends across the night sky as a soft, pale arc of light, its brightness uneven, its texture filled with stars, gas, and dust. Within its wide spiral arms, gravity gathers clouds into knots of matter, where new stars are born and others die. Among these vast regions, the northern arm, sometimes called the Cygnus arm, holds particular interest for astronomers. It is one of the great structures of the galaxy, curving outward in a broad sweep more than tens of thousands of light-years from the galactic center. The arm is filled with glowing nebulae, dark lanes of interstellar dust, and a scattering of high-mass stars that live quickly and end violently. Each of these stars burns through its fuel at a rate millions of times faster than the sun, driving out fierce winds and bathing their surroundings in ultraviolet radiation. Here, turbulence and silence coexist. Shock waves from past supernovae ripple through gas clouds, compressing them into new seeds of formation. Across these regions, motion is almost imperceptible on a human scale, but constant on a cosmic one. The patterns of light that reach Earth tonight began their journey when early humans still painted animals on cave walls. The Milky Way's arms do not stand still. They rotate around the galactic center over immense spans of time, completing a single revolution in hundreds of millions of years. From Earth's position in one of the interior arms, astronomers can trace the structure of the Cygnus region through radio-optical and X-ray signals. The region lies toward the constellation of the Swan, an area rich in stellar associations and massive binaries. In this part of the sky, the density of young stars is unusually high, and so are the remnants of those that have already collapsed. The balance between creation and destruction is visible here more than in most places, a reminder that the galaxy is both nursery and grave. When observers look into the band of the Milky Way near Cygnus, they are looking into one of the most crowded neighborhoods of the galaxy, a region heavy with history and light. Within the Cygnus arm, countless systems orbit in quiet isolation, their fates determined by mass and proximity. Many are binary systems, pairs of stars bound by gravity, moving in long invisible curves around one another. In such pairs, mass transfer can alter evolution profoundly. The heavier star may age and die first, leaving a remnant that continues to interact with its companion. These interactions can produce some of the most luminous phenomena in the galaxy, particularly when one object becomes compact, a neutron star or a black hole. For decades, astronomers suspected that such remnants should exist, though no direct proof was at first available. The idea of a gravitational body so dense that not even light could escape remained theoretical, a mathematical prediction that awaited observational confirmation. The northern arm, with its abundance of massive short-lived stars, provided many possible birthplaces for such an object. The conditions here are ideal dense molecular clouds to form stars, frequent supernova explosions, to create compact remnants, and enough binary systems for some to survive the violent deaths of their primary stars. The result is a sky rich with signals beyond the visible range. Radio telescopes map out vast plumes of hydrogen. Optical telescopes reveal clusters and bright blue supergiants. X-ray observatories detect intense points of energy, where gravity and matter combine in extreme ways. Among these X-ray sources, one in particular stands out, a single bright point, that flickers and varies, whose position lies in the heart of the Cygnus constellation. At first it appears as one among many another coordinate in a catalogue of luminous spots. Yet over time this single point will reveal an extraordinary story. Its radiation is so powerful that even from thousands of light years away, it can outshine entire star clusters in the X-ray band. It is an object that behaves unlike any ordinary star, changing brightness, irregularly, sometimes within seconds. The light is not steady because the energy does not come from fusion, but from matter falling inward under intense gravity. This region, where ordinary physical rules begin to strain, will later be named Cygnus X-1. It resides in the same galactic arm that Earth inhabits, though separated by more than 6,000 light-years. From our vantage it lies near the Northern Cross pattern, formed by the brighter stars of the constellation. The name combines its celestial location with the type of radiation by which it was first found: X-rays, the signature of extreme heat and violent motion. Long before this name was attached, the energy itself was reaching Earth, passing unnoticed through its atmosphere, until the development of space-based instruments made such detection possible. To understand the setting of this source, one must imagine the local environment of the Cygnus region. Around the source are other massive stars and clusters, each shedding material into space. Stellar winds sweep through interstellar gas sculpting cavities and filaments. The average temperature of this environment is far below freezing by terrestrial standards. Yet within certain boundaries, temperatures rise into the millions of degrees, driven by magnetic fields and radiation pressure. Light travels unimpeded through most of the space here, but near compact objects gravity bends its path. Dust grains scatter and absorb visible light, hiding much of the region from optical view. Infrared and radio observations reveal structures invisible to the eye: jets, bubbles, and remnants of ancient explosions. This mixture of matter and energy forms the background for Cygnus X-1. The system lies within a dense and active portion of the arm, surrounded by clouds that bear traces of both creation and decay. The presence of a high-mass X-ray source here is not an accident. It is the natural outcome of stellar evolution, in a place where massive stars are common. Each generation enriches the interstellar medium with heavier elements forged in their cores, and the next generation forms from that material, repeating the cycle. When viewed from a distance, the region glows softly in many wavelengths, a map of ongoing transformation. Against this glowing field, Cygnus X-1 is a small, nearly point-like source, but its intensity and variability distinguish it from the quieter stars around it. Even without knowing its nature, astronomers recognized it as something extraordinary. The story of Cygnus X-1 begins then not with the black hole itself, but with the galactic environment that made it possible. In the northern arm, where the forces of gravity, radiation, and time constantly reshape the interstellar landscape, stars are born massive and die young. Each death leaves behind an echo, sometimes a neutron star, sometimes a black hole. Among these echoes, Cygnus X-1 will stand out as the first unmistakable sign that the universe does indeed produce objects from which no light can escape. Its light, paradoxically, will be the proof of its darkness. For now the region lies serene in its vastness, with only the faint, steady hum of X-rays marking the presence of something deeper to come. The constellation of Cygnus stretches high across the northern sky during late summer evenings, its brightest stars forming the figure of a swan in flight. The long neck, sweeping wings, and trailing tail have been recognized since ancient times, but the shape also serves as a map for astronomers seeking the hidden phenomena that lie within the Milky Way's dense band. Each of its bright points is a sun many times more luminous than our own, embedded in a crowded field of fainter stars and dust. To the eye, Cygnus seems calm, a distant pattern unchanging against the dark. Through instruments sensitive to invisible wavelengths, however, it reveals a place of violent energy. The region contains multiple stellar nurseries, remnants of supernova explosions, and an unusual number of high-energy sources invisible to the human eye. Among them is Cygnus X-1, one of the most intense X-ray emitters known. Its presence cannot be discerned by starlight alone. The optical view shows only a single blue star. Yet above the atmosphere, detectors register the rapid flickering pulse of radiation that betrays something hidden and extreme. When astronomers first studied the constellation with radio and X-ray instruments, they catalogued sources by location rather than by nature. The label Cygnus X-1 simply meant the first X-ray source detected within Cygnus. At the time, few could guess its true character. Early X-ray astronomy was in its infancy, relying on rockets that spent only minutes above the absorbing blanket of Earth's atmosphere. These brief observations revealed dozens of cosmic X-ray sources scattered across the sky, but their positions were imprecise. The detection of one particularly bright emitter in the direction of Cygnus in the early 1960s began a long chain of investigation. As instruments improved, its coordinates were refined, and telescopes on the ground sought any star that might correspond to it. The task was not simple. The Milky Way's dust veils much of the light in this direction, and many massive stars crowd the same region. Identifying which of them coincided with the X-ray emission required patience and precision. By the early 1970s, observers had narrowed the possibilities to a single candidate, a brilliant blue supergiant known as HDE Cygnus 68868. This star shone clearly in visible light, massive and hot, radiating an intense blue-white glow. But the X-rays detected from its direction could not be explained by any normal stellar process. The radiation was too strong, too variable, and concentrated in too small a region. Something unseen was feeding upon the star's outer layers, releasing gravitational energy as heat and light. The identification of HDE 2226868 marked the first time a visible star had been associated with an invisible companion of extraordinary mass. By analysing the star's spectral lines, astronomers could measure its motion toward and away from Earth. These shifts followed a regular cycle, implying that it orbited around an unseen partner roughly every 5.5 days. The orbital curve suggested that the hidden companion must be at least several times more massive than the Sun, too heavy to be a neutron star, too compact to be a normal star. The conclusion reached with cautious deliberation was that the object in Cygnus X-1 must be a black hole. It would become the first such object widely accepted as real, not merely hypothetical. To imagine its position in the sky is to look along the Milky Way's dense midplane toward a region about 6,000 light-years from Earth. The location lies near the bright star Cassini in the wing of the celestial swan. While the naked eye sees only the star pattern, X-ray telescopes reveal a second hidden universe layered atop the visible one. In that invisible universe, Cygnus X-1 dominates its surroundings. It is not the brightest X-ray source in the galaxy, but its steadiness and accessibility make it among the best studied. Its discovery opened a path that would later lead to the detection of hundreds of other X-ray binaries and black holes throughout the Milky Way. The constellation itself is home to many such systems. Cygnus X-2 and Cygnus X-3, detected later, each involve compact remnants feeding on companion stars. But Cygnus X-1 holds a special place because it was the first to reveal, through precise measurement, the unmistakable signature of a black hole's gravitational pull. This identification confirmed decades of theory and provided a natural laboratory for studying physics under extreme conditions. In the same field of view, the North American nebula glows faintly in hydrogen light. Young star clusters scatter along dark dust lanes, and expanding shells mark the sites of past supernovae. Cygnus, for all its serenity to the eye, is a theatre of birth and death. The swan gliding across the Milky Way is a symbol drawn over one of the galaxy's most energetic regions. Observing it requires instruments both in space and on the ground. X-ray satellites detect the high-energy radiation that cannot penetrate the atmosphere, while optical telescopes follow the visible companion's motion. Together they provide a composite picture of a binary system bound by gravity, yet profoundly unequal in nature. One member, the blue supergiant, lives a short luminous life, its surface heated to tens of thousands of degrees, and its mass measured in dozens of suns. The other, invisible but heavier, has collapsed beyond any physical surface, existing only as a region where space and time are curved inward. The light from the visible star fluctuates subtly as it orbits its brightness, dimming when the compact object passes in front and brightening again as it moves behind. The X-ray emission varies more dramatically, reflecting the chaotic flow of matter near the black hole's edge. In mapping the location and behavior of Cygnus X-1, astronomers gained not only a specific object, but an entire field of study. The constellation became synonymous with the exploration of high-energy astrophysics. Each refinement of observation, from early balloon-borne detectors to sophisticated space observatories, added detail to the picture, changes in luminosity, spectral shifts, radio jets extending into space. The region's story mirrors the progress of technology, each generation seeing more deeply into the same patch of sky. Yet even as the instruments became sharper, the source retained elements of mystery. Its variations defied simple patterns, its energy output fluctuated unpredictably, and the mechanisms driving its jets and radiation remained complex. In the quiet of a clear night, the constellation Cygnus still crosses the sky, as it has for millennia, appearing calm and graceful. Beneath that calm lies one of the most dynamic systems in the galaxy. Through that patch of light, energy streams across space at all wavelengths, unseen, but measurable, constant and powerful. The discovery of Cygnus X-1 transformed the swan from a poetic symbol into a gateway to understanding gravity's most extreme form. It remains there tonight, faintly aligned with the Northern Cross, invisible to ordinary eyes, yet endlessly watched by those who measure the unseen. The discovery of Cygnus X-1 began with the rise of a new kind of astronomy, one that could see the universe through X-rays rather than visible light. In the early 1960s, this field was only beginning to take shape. Traditional telescopes, even the most powerful optical instruments, were blind to high-energy radiation. Earth's atmosphere blocks X-rays, completely a shield that protects life, but hides much of the universe's energetic behavior. Only by lifting detectors above the atmosphere could astronomers detect the faint signals arriving from beyond. Sounding rockets rising for a few minutes above the stratosphere provided the first glimpses. In June of 1964, one of these brief missions revealed a series of bright X-ray sources across the sky, each appearing as a point of concentrated energy. Among them was a source in the direction of Cygnus, later named Cygnus X-1. Its signal was strong, steady, and distinct. Though the instruments then in use could not pinpoint its exact position, they marked it as one of the brightest cosmic X-ray emitters known at the time. The discovery surprised scientists because such radiation could not come from ordinary starlight. Only extremely hot gas heated to millions of degrees could produce the intensity observed. The presence of such heat implied an enormous release of energy from a very compact region. As the years passed, more sensitive detectors confirmed that Cygnus X-1 was real and persistent. Satellite missions launched by the United States and the Soviet Union in the late 1960s and early 1970s recorded its fluctuating intensity. Sometimes it grew brighter, sometimes it dimmed, varying over minutes and hours. These rapid changes suggested that the source must be small, no larger than a few tens of kilometers across, because larger objects cannot change brightness so quickly. The pattern of variability was unlike anything known in stellar physics. Scientists began to consider that the energy might come from gas falling onto an extremely dense object. Theoretical work on black holes, which had long remained abstract, suddenly gained relevance. Here was an object that seemed to fit the predictions invisible in ordinary light, drawing in matter and converting gravitational energy into radiation. The process of detection depended on instruments that were crude by later standards but revolutionary for their time. Gas-filled detectors aboard rockets counted individual photons, while early satellites such as Uhuru and Ariel measured their energies and timing. These counts were translated into brightness scales and plotted against time. The data came in as numerical patterns rows of changing intensities that revealed unseen violence in the cosmos. In this way, astronomers began to map a sky that had never before been visible. Cygnus X-1, persistent and bright, became a focus of observation for multiple missions. Each pass of a satellite refined its position, narrowing the possible optical counterparts within the constellation. Once its coordinates were known, more precisely attention turned to identifying what visible star might share its location. The optical telescopes of the day, equipped with photographic plates, captured the bright blue star HDE 2226868 within the same region. This correspondence did not at first prove a physical connection, but the coincidence was striking. When astronomers studied the star's light spectrum, they noticed periodic shifts in its lines indicating orbital motion. The star was wobbling, pulled by the gravity of something unseen. The orbital period, about 5.5 days, matched the timing of certain X-ray fluctuations, strengthening the case for association. By calculating the orbital speed and applying the laws of motion, scientists could estimate the mass of the invisible companion. The result was astonishing. It had to be at least several times the mass of the Sun, yet produced no visible light. The possibility that it was a black hole divided opinion at first. Some argued for an unusual kind of neutron star or an exotic stellar core. Others pointed out that only a black hole could match the mass and compactness required. As more data accumulated, the argument shifted toward acceptance. By the mid-1970s, Cygnus X-1 was widely recognized as the first strong candidate for a stellar mass black hole. Its confirmation gave substance to a concept that until then had existed only in mathematical form. The idea that gravity could trap light had been proposed centuries earlier, but it was through X-ray astronomy that such objects entered observation. The detection of X-rays from Cygnus X-1 also demonstrated that the universe is far more dynamic than once imagined. Stars long thought to be stable beacons could interact violently, exchanging material and energy. The X-ray light from Cygnus X-1 revealed matter being heated and torn apart under immense gravitational forces. The radiation we see is only a tiny fraction of the energy involved. Most is swallowed by the invisible object itself. The variations in brightness carry information about how matter behaves as it approaches the limit of escape. For scientists, each fluctuation became a clue to the physics of extreme gravity. The early era of X-ray observation brought challenges as well. Instruments were limited in resolution, and cosmic sources often overlapped. Background radiation, solar flares, and electronic noise complicated measurements. Yet the signal from Cygnus X-1 persisted through every observation. It was unmistakable and stable over years, confirming that it was not an artifact but a genuine celestial object. Later missions, most notably NASA's High Energy Astronomical Observatory and ESA's ExoSat, provided clearer data showing distinct spectral states, times when the source emitted softer X-rays, and times when it shifted to harder, more energetic ones. These changes indicated that the accretion process, the flow of matter onto the compact object, was variable. Sometimes gas fell smoothly. At other times turbulence dominated, creating short bursts and flares. Each observation added detail to a growing portrait. The source's average energy output was equivalent to millions of suns, yet concentrated within a volume smaller than Earth. Its spectrum revealed gas at temperatures exceeding tens of millions of degrees. No solid surface could exist under such conditions. The only consistent explanation was that matter was being pulled into a region where gravity overwhelmed all other forces. The disk of infalling gas unseen directly radiated in X-rays as friction and compression heated it. This model matched the data remarkably well, and became the template for understanding other X-ray binaries discovered later. Cygnus X-1 thus stands as a landmark in the history of observational astronomy. It bridged theory and evidence, showing that black holes were not mere abstractions but active participants in the cosmos. Its discovery also transformed the methods of astrophysics, proving the value of exploring wavelengths beyond visible light. With each new satellite, the view sharpened higher, resolution, faster timing, broader coverage. Yet even as the details improved, the essential mystery remained: the unseen engine at the system's core. What had once been a theoretical boundary became an observable fact, written not in starlight but in invisible radiation. Today, when telescopes monitor the same patch of sky, they still register the steady pulse of Cygnus X-1. Its signal has crossed more than 6,000 light-years to reach Earth, carrying the history of a system that began long before humans existed. The object that once startled scientists now serves as a standard reference, its characteristics used to test models of gravity, magnetism, and radiation. Still, the original moment of recognition, the first detection of X-rays from a quiet point in Cygnus, remains one of the milestones of modern astronomy. From that signal, a new picture of the universe emerged, one filled not only with stars and galaxies, but with invisible depths where energy and matter obey the most extreme laws of nature. The recognition that Cygnus X-1 belonged to a binary system transformed it from a mysterious light source into a detailed physical object. The visible star, catalogued as HDE 268 was classified as a blue supergiant of spectral type 09.7, one of the hottest and most massive types known. Its surface temperature exceeds 30,000 degrees Celsius, and its luminosity surpasses the Sun's by nearly 500,000 times. Such a star cannot endure for long. It burns hydrogen into helium at an extraordinary rate, losing material through an intense stellar wind that streams outward into surrounding space. Each second it sheds millions of tons of gas, forming an expanding envelope that drifts across the binary orbit. That outflow does not vanish into emptiness. It becomes the lifeblood of the system, drawn toward the compact companion whose gravity bends the flow into a spiraling path. The two objects orbit one another in a tight dance, lasting about 5.5 days. The visible star dominates the pair in brightness and size. Its radius stretches several dozen times that of the Sun. Yet the unseen companion exerts the stronger gravitational pull. Astronomers studying the periodic motion of the supergiant spectral lines determined that the invisible object must weigh roughly 15 times as much as the Sun, far too massive to be any known neutron star. This calculation provided the decisive clue. Only a black hole, a region of space-time whose escape velocity exceeds the speed of light, could contain so much mass within so small a volume. The discovery made Cygnus X-1 the first confirmed stellar mass black hole in history. The orbit of the system is not perfectly circular, but slightly elongated, causing the distance between the two bodies to change over time. At their closest approach, the star's outer atmosphere is strongly distorted by tidal forces. Gas from its surface is pulled outward, forming a stream that bends toward the companion's gravity well. This material does not fall directly inward. As it approaches, conservation of angular momentum forces it to spiral, flattening into a thin rotating structure known as an accretion disk. Within this disk, friction and compression convert gravitational energy into heat-producing temperatures of millions of degrees. The resulting radiation emerges primarily as X-rays. What telescopes detect from Earth is the signature of this process, a continuous transformation of matter into energy at the threshold of a black hole. Although the supergiant is easily visible in optical wavelengths, its relationship with the black hole can only be traced through motion and radiation. Over each orbit, the star moves alternately toward and away from Earth, its spectral lines shifting slightly due to the Doppler effect. By tracking these shifts, scientists can measure velocity and derive the masses of both components. These measurements reveal a system in balance with the black hole, drawing material from the star's outer layers, while the star's radiation pressure and wind resist that pull. The equilibrium is dynamic rather than stable. Over time, as the star continues to lose mass, the rate of transfer fluctuates, altering the intensity of the X-ray output. In optical light, observers see a brilliant blue point, but in high-energy bands, Cygnus X-1 appears as a flickering beacon. Its emission varies unpredictably, sometimes brightening sharply in short bursts. These fluctuations arise from turbulence within the accretion disk, where magnetic fields twist and reconnect, releasing bursts of energy. The disk's inner edge orbits at nearly half the speed of light, and any change in density or temperature produces immediate changes in radiation. Because the system is so compact, variations can occur on timescales of milliseconds. Each pulse carries information about the structure of the disk and the behavior of matter under intense gravity. For astronomers, Cygnus X-1 became a natural laboratory for testing models of binary evolution. The presence of a massive companion star meant that the black hole must have formed from an even heavier progenitor, perhaps a star with more than 40 times the Sun's mass. When that star ended its life, it likely collapsed directly into a black hole, without a visible supernova, its outer layers falling inward instead of exploding outward. The survival of the binary pair after such a collapse is remarkable. The gravitational bond endured despite the violence of stellar death. This endurance suggests that the system lost relatively little mass during the event, an observation that influenced later theories of how black holes form. The visible star, though luminous, lives under constant strain. Radiation pressure from its interior pushes outward, while gravity from the companion pulls inward. The result is an elongated shape, slightly egg-like, with the long axis directed toward the black hole. The surface temperature is not uniform. Regions facing the black hole may be heated by X-rays, creating localized changes in brightness. Astronomers studying these variations have reconstructed the system's geometry, confirming that the two bodies are separated by a distance of only about 1/5 the width of Mercury's orbit around the Sun. Within that narrow space, gas flows continuously, forming a bridge of ionized material between the two. The detection of these flows relied on both spectroscopy and timing analysis. Instruments aboard satellites such as Uhuru Aerial and later Chandra and XMM Newton, measured subtle periodicities in X-ray output, while ground-based telescopes tracked the visible star's color and luminosity. Together, these observations revealed that the accretion process is not steady, but pulsating, driven by the interplay of wind pressure, magnetic fields, and orbital motion. Sometimes the flow thickens, producing a bright flare. At other times it thins, allowing the emission to subside. Over longer intervals, the system passes through distinct spectral states known as high, soft, and low hard, characterized by different temperature distributions in the disk. These states reflect the changing balance between thermal and non-thermal processes near the black hole. The binary nature of Cygnus X-1 also allowed for precise distance measurement. By modeling the star's intrinsic brightness and comparing it with its apparent magnitude, scientists estimated a distance of about 6,000 light-years. Later parallax measurements using radio interferometry refined that value further. Knowing the distance enabled accurate calculations of energy output, confirming that the system radiates roughly 100,000 times more power than the Sun across all wavelengths. Despite this, the black hole itself remains invisible. Its presence is known only through the effects it exerts on nearby matter. The pairing of a luminous star and a dark companion also creates observable polarization in light. X-rays scattered by electrons in the accretion disk acquire a specific orientation that depends on the system's geometry. Measurements of this polarization have provided clues about the disk's inclination and the black hole's spin axis. Such data helped confirm that Cygnus X-1's black hole rotates, rapidly dragging spacetime around with it in a phenomenon known as frame dragging. The combination of orbital motion accretion dynamics and relativistic effects makes the system one of the most studied objects in the sky. To the human eye, none of this is visible. The region of Cygnus that holds the system looks no different from the rest of the Milky Way's crowded band. Yet behind the calm blue light of a single star lies an engine of immense energy, a place where matter crosses the boundary between existence and oblivion. The binary system embodies the balance of forces that shape the universe: radiation, pushing outward, gravity pulling inward, energy released as matter falls toward the limit of no return. For half a century, its steady rhythm of motion has remained unchanged, continuing the quiet exchange that began when the black hole was born. The orbit endures, the star still burns, and far away on Earth, telescopes continue to record the invisible light of their interaction. From the moment the binary nature of Cygnus X-1 was confirmed, the question that dominated scientific attention was how to measure what could not be seen. The object's mass, size, and behavior had to be inferred entirely through the effects it produced on its companion and on the radiation surrounding it. The effort to quantify these effects became one of the most detailed exercises in indirect measurement in modern astronomy. Each observation, whether optical, radio, or X-ray, provided a piece of the same puzzle, allowing scientists to reconstruct the physical nature of the invisible body. The key was motion. The visible star's orbit followed a clear rhythm, and from that rhythm came the first precise numbers: orbital period, radial velocity, and amplitude. Applying the laws of celestial mechanics, astronomers determined that the unseen partner's mass must be greater than 3 solar masses, the theoretical upper limit for a neutron star. Later refinements increased the estimate to around 15, confirming that only a black hole could account for such density. Yet even as this conclusion gained acceptance, the black hole itself remained an abstraction, a gravitational field rather than a tangible surface. To visualize the system, one must imagine a center of gravity so intense that space itself curves around it. Within a few tens of kilometers of the center lies the event horizon, the boundary from which no light escapes. Surrounding that boundary, the infalling gas forms a disk of extraordinary brightness. This disk emits the X-rays first detected in the 1960s. The brightness fluctuates because the rate of accretion changes, controlled by the stellar wind strength and by magnetic turbulence within the disk. Instruments orbiting Earth record these variations as sequences of pulses and flickers, translating them into numerical curves that describe energy output over time. Each curve carries the imprint of the physical processes at work close to the event horizon. Astronomers also sought to determine how fast the black hole spins. In general, relativity rotation twists spacetime, dragging nearby matter into motion. Measuring this spin required detailed modelling of the X-ray spectrum, particularly the broadened ion emission lines produced when photons escape from the inner disk. The distortion of these lines, shifted and stretched by gravitational redshift, offered a means to gauge the rotational velocity. The results revealed an object spinning near the theoretical limit, completing several hundred rotations per second. Such rapid rotation indicates that much of the angular momentum of the original massive star survived the collapse. It also explains the powerful magnetic and relativistic effects observed near the disk's inner edge. Because no single telescope could capture all these phenomena, a global network of instruments worked together. Ground-based optical observatories tracked the supergiant's orbit, while radio arrays measured the tiny positional wobble of the system across the sky. X-ray satellites recorded high-energy radiation, and ultraviolet detectors aboard space telescopes filled in the intermediate wavelengths. From this multi-wavelength approach emerged a coherent model, a massive blue supergiant losing matter to a rapidly spinning black hole through a focused stellar wind, the accreting gas forming a hot thin disk that radiates in X-rays. The precision of these measurements continued to improve through the late 20th and early 21st centuries. In 2011, parallax data from radio interferometry provided the most accurate distance yet, about 6,070 light-years, allowing a recalculation of mass and luminosity with reduced uncertainty. Each refinement narrowed the margins of error, reinforcing the reality of the black hole beyond theoretical doubt. By now, Cygnus X-1 was not only the first, but also one of the best characterized stellar mass black holes known. Even with such precision, questions remained about how mass transfer proceeds from the supergiant's wind to the accretion disk. Observations revealed that the wind is not uniform but clumped, forming denser regions that occasionally enhance the accretion rate. When these clumps pass through the line of sight, X-ray intensity dips, briefly producing a characteristic pattern of absorption events. These dips serve as probes of the wind structure, revealing its temperature, ionization, and velocity. Over time, a portrait has emerged of a dynamic environment in which the black hole feeds irregularly on the changing outflow of its companion. The feedback between radiation and wind further complicates the picture. The intense X-ray emission ionizes nearby gas, altering its opacity and slowing the wind, which in turn affects the accretion rate. This cycle repeats continuously, maintaining a delicate balance between inflow and outflow. Another line of inquiry concerns the geometry of the accretion flow itself. At moderate distances from the black hole, gas orbits in nearly circular paths, but closer in, strong gravity and magnetic forces cause the flow to warp and twist. Above the disk lies a region known as the corona, a cloud of high-energy electrons that scatter X-rays into even higher energies. By analyzing changes in the spectrum, scientists have inferred the corona's temperature and size. It appears to extend only a few tens of kilometers above the disk, yet its influence on the observed emission is profound. The interplay between disk and corona shapes every fluctuation recorded by telescopes. The drive to measure Cygnus X-1 has always been more than an attempt to catalogue one object. It is a test of physical law under conditions unattainable on Earth. The data derived from it have been used to refine equations of accretion physics, to test predictions of general relativity, and to calibrate other X-ray binaries across the galaxy. Each new measurement extends the framework built from the first crude rocket detections decades earlier. The continuity of observation spanning generations of instruments reflects the long timescales of both cosmic and human persistence. While the black hole remains invisible, its gravitational influence is unmistakable. The orbit of the companion star provides a continuous measure of its pull, a silent confirmation of Einstein's geometry at work. Even the light from the supergiant carries the mark of proximity to the abyss, subtle broadening of spectral lines, irregularities in brightness and periodic changes in color temperature. Every measurable quantity serves as an indirect signature of the unseen mass. The precision required for such measurements is extraordinary. Even small errors in angle or timing could lead to large differences in calculated mass. Yet successive studies using independent techniques have converged on nearly identical values. The consistency itself is evidence of the object's authenticity. The human dimension of this measurement effort is no less remarkable. Over 60 years, hundreds of scientists and engineers have contributed to building and operating detectors capable of capturing light that never reaches the ground. The results are transmitted across thousands of kilometers, processed into datasets, and compared with models that describe how matter moves near a gravitational singularity. Cygnus X-1, once a mysterious flicker on a strip of film, now serves as one of the most carefully quantified systems in astrophysics. Still, despite the precision of numbers, the essence of what lies beyond the event horizon remains unknowable. Measurements stop at the boundary of escape, leaving only inference and mathematics to describe what follows. In the sky, the region continues to emit its steady radiation, unchanged to the eye. The black hole neither brightens nor dims on human timescales, and the companion star remains visible in the small telescopic field where both coexist. What began as an unidentified point of high-energy light has become the benchmark against which others are measured. The path from discovery to understanding runs entirely through observation, through the steady accumulation of data that turns mystery into knowledge, while leaving the core of wonder intact. Cygnus X-1 stands as both object and instrument, a single binary system teaching the physics of the universe's most hidden places. The visible companion of Cygnus X-1 HDE 226868 dominates the system in appearance but lives in the shadow of forces that will determine its fate. This blue supergiant, with a mass of about 40 times that of the Sun, belongs to a class of stars that exhaust their fuel quickly and die young. Its outer layers glow with temperatures exceeding 30,000 degrees, releasing intense ultraviolet radiation that drives the stellar wind upon which the black hole feeds. The wind streams outward at thousands of kilometers per second, a continuous flow of charged particles accelerated by radiation pressure from the star's luminous surface. It is this flow that sustains the X-ray brightness of the system, converting the star's mass into the energy observed by telescopes on Earth. The wind structure is complex. It is not a uniform current, but a turbulent cascade of denser clumps separated by thinner gas. Each clump carries a fraction of the total mass loss, and as these clumps travel across the orbit, the black hole captures some of them, while others drift away into interstellar space. When a clump crosses the line of sight between the X-ray source and the observer, the radiation dips briefly before returning to normal. These characteristic fluctuations, lasting minutes or hours, trace the invisible wind's passage, allowing astronomers to model its density and temperature. The supergiant's proximity to the black hole shapes its surface and its atmosphere. Gravitational forces stretch the star into an ellipsoidal form, its outer layers pulled slightly toward the compact object. From one hemisphere, gas flows more readily than from the other, forming a focused stream rather than a symmetrical wind. This directed outflow spirals inward under gravity, eventually settling into the accretion disk that circles the black hole. The process is continuous but unstable. Variations in the star's rotation magnetic field and internal convection alter the wind's speed and density, which in turn modulate the rate of accretion. These feedback loops create the irregular flickering that defines Cygnus X-1's light curve. The interaction between star and black hole is not one of quiet coexistence but of ongoing exchange. The star loses mass through its wind while the black hole gains it through accretion. Over millions of years, this transfer can change the balance of the system. The star's decreasing mass alters the orbit's dynamics, gradually widening the separation and lengthening the period. Yet the rate of change is slow compared with human lifetimes. For now, the system remains locked in its present configuration, stable enough for detailed observation, yet dynamic enough to exhibit constant variability. The radiation from the black hole influences the star's wind in subtle ways. When the X-ray flux rises, the surrounding gas becomes ionized, its atoms stripped of electrons. Highly ionized gas absorbs less radiation from the star's ultraviolet light, weakening the radiation pressure that drives the wind. As a result, the flow slows down, reducing the accretion rate and causing the X-ray emission to drop. When the gas recombines, the wind strengthens again. This interplay forms a self-regulating cycle that keeps the system from running away into either extreme. The balance is delicate. A slight increase in one component alters the other, producing the complex patterns of variability seen in the data. At optical wavelengths, HDE TOSUNSTU 68D68 appears almost serene, its blue light constant to the eye. But spectroscopic studies reveal changes in its outer layers that mirror the unseen activity nearby. Ultraviolet lines broaden and shift as the wind accelerates. Emission features strengthen when gas near the black hole glows under X-ray illumination. In some phases, material flows back toward the star, creating temporary absorption features that mark the oscillation of matter between the two bodies. The stellar atmosphere becomes both supplier and witness to the accretion process. The star's immense energy output also bathes the system in radiation that interacts with the accretion disk. Photons from the star strike the outer disk, heating it, and producing a faint optical glow in addition to the dominant X-rays. This reprocessed light provides another diagnostic of the system's geometry. By measuring the time delay between X-ray flares and optical responses, astronomers can estimate the size of the disk and its distance from the star. Such measurements confirm that the disk extends millions of kilometers from the black hole, thin and hot, with a surface temperature that falls from millions of degrees near the center to only a few thousand at its outer edge. Within the broader context of stellar evolution, HDE TOSUNSTU 6868 represents a transitional stage. Its core fuses helium into heavier elements, while its outer layers expand and lose mass. Over time, the star will continue to shed material until its own internal balance fails. If it survives long enough, it may collapse into another compact object, possibly a neutron star or another black hole, forming a double system of two gravitational singularities. For now, the partnership between blue supergiant and black hole endures a living example of the extremes that stellar life can reach. Understanding such stars also sheds light on how heavy elements are distributed throughout the galaxy. The wind from a massive star carries carbon, nitrogen, and oxygen produced in nuclear fusion, enriching the interstellar medium from which new generations of stars will form. Even as it feeds the black hole, the star contributes to the cosmic cycle of matter. The captured portion disappears beyond the event horizon, but the rest escapes into space, joining the diffuse gas that fills the Milky Way's arms. In this way, the system participates simultaneously in destruction and renewal. The supergiant's light, though diminished by distance and interstellar dust, still reaches Earth with enough strength to be studied in detail. Its spectrum serves as a record of both its own properties and the influence of its dark companion. Variations in color and intensity have been tracked for decades, showing remarkable consistency over time. The star's mass loss rate remains high, its rotation fast, and its temperature stable within narrow limits. This persistence allows researchers to test long-term models of stellar wind physics, confirming that even under the influence of a nearby black hole, the fundamental principles of radiation and gravity hold. For all its power, the star is temporary. Massive stars like HDE 226868 burn through their fuel quickly, living only a few million years compared to the Sun's 10 billion. When its core energy source is exhausted, the balance of pressure and gravity will collapse, leading to another violent transformation. The black hole will survive unchanged, while the visible star will vanish, perhaps leaving behind a second compact remnant. The two could merge, emitting a burst of gravitational waves detectable across the galaxy. For now, that future remains distant. What observers see today is a snapshot of a system caught in mid-evolution, a bright hot star locked in orbit with the invisible outcome of another's death. Through the steady accumulation of data, the character of HDE 226868 has become clear, a massive, luminous, short-lived supergiant shedding its outer layers into space, while circling a gravitational abyss. Its brilliance lights the field for human eyes, but its destiny lies in the same direction as its companions, toward collapse, toward invisibility, toward the quiet gravity that rules the center of the system. Cygnus X-1 endures as a union of opposites, radiance and darkness, expansion and infall creation and loss, all held together by the invisible geometry of spacetime itself. When gas escapes from the surface of HDE 226868 and enters the gravitational reach of the black hole, it begins a transformation that ends in extreme heat and radiation. The transfer of matter does not occur as a simple fall. It unfolds in spirals shaped by the balance of gravity, angular momentum and magnetic forces. As particles move inward, collisions and friction cause them to lose energy, and angular velocity settling gradually into a rotating disk that encircles the black hole. This disk, called the accretion disk, is the luminous heart of Cygnus X-1, the structure that produces most of its observed energy. The outer edge of the disk lies where the black hole's gravity first overcomes the star's wind. Here, gas is still relatively cool, glowing faintly in ultraviolet light. Closer to the center, the temperature rises sharply as particles accelerate and compress. The heat becomes so intense that atoms ionize completely and radiation emerges as X-rays. Within the inner few hundred kilometers, the energy density reaches levels that cannot be reproduced in laboratories on Earth. Each particle completes thousands of orbits per second, and the light emitted at one moment can be redshifted or blueshifted depending on the disk's rotation and the observer's line of sight. From Earth, telescopes detect the integrated result of these motions, a continuous spectrum of high-energy radiation, modulated by turbulence. The disk itself cannot be seen directly, but its effects are unmistakable. The brightness of Cygnus X-1 fluctuates as the disk's density changes, sometimes rising to peaks where the X-ray flux doubles within seconds. These variations are the product of magnetic instabilities, where tangled field lines in the plasma reconnect and release sudden bursts of energy. Such reconnection events occur constantly, giving the disk a restless, flickering character. Astronomers interpret this behavior as evidence of magneto-rotational turbulence, a process that allows gas to transfer angular momentum outward while moving inward under gravity. Without this mechanism, the accretion flow would stall. With it, material can reach the black hole's edge, releasing gravitational energy as light before disappearing beyond the event horizon. The accretion disk is a dynamic structure continuously renewed as new matter arrives from the star's wind. Its thickness depends on temperature at high accretion rates. It puffs up into a warm, geometrically thick disk. When the inflow subsides, it cools and flattens. Observations show that Cygnus X-1 alternates between two principal states. In the low hard state, the disk is cooler and the emission dominated by hard X-rays from the corona. In the high soft state, the disk brightens and soft X-rays prevail. Transitions between these states can occur over days or weeks, triggered by changes in mass transfer or magnetic configuration. Each transition reveals how delicately balanced the system is, with small perturbations leading to large changes in observable energy output. The physics of accretion is a story of conversion gravitational potential energy transformed into radiation. As matter approaches the event horizon, up to 10% of its rest mass can be released as light, a vastly more efficient process than nuclear fusion in stars. In Cygnus X-1, this energy radiates outward as a steady glow, in X-rays sometimes extending into gamma rays. The innermost part of the disk, only a few times the size of the black hole itself, is where most of the emission originates. Here, general relativistic effects become significant. The curvature of space-time bends light paths, distorts emission lines, and delays signals depending on the observer's angle. By modeling these distortions, scientists can estimate the black hole's spin and the radius of the innermost stable orbit. Measurements indicate that the black hole in Cygnus X-1 rotates close to the maximum allowed by relativity, meaning that its surface, if such a surface could exist, would move through space at nearly the speed of light. The environment around the disk is equally complex. Above and below its plane lies a tenuous atmosphere of hot electrons called the corona. This corona scatters lower energy photons from the disk into higher energies through a process known as inverse Compton scattering. The result is a power law tail in the X-ray spectrum extending to hundreds of kiloelectron volts. The corona's structure changes with time, sometimes shrinking to a compact region near the black hole, sometimes expanding to encompass much of the inner disk. When it expands, the system's overall X-ray emission hardens. When it contracts, the spectrum softens. These changes can occur rapidly, giving Cygnus X-1 its characteristic variability. Radio observations add another dimension to the picture. Interferometers have detected faint jets extending from the vicinity of the black hole, narrow streams of particles moving outward at relativistic speeds. These jets are not constant, but appear during particular accretion states linking the behavior of the disk and corona to larger-scale outflows. The origin of these jets remains one of the system's enduring puzzles. They seem to arise when magnetic fields anchored in the disk tap into the black hole's rotational energy launching matter along the poles in collimated beams. Even though these jets carry only a small fraction of the accreted mass they transport, enormous energy influencing the surrounding interstellar medium. Understanding the accretion disk of Cygnus X-1 has required a combination of theory, simulation, and observation. High-resolution X-ray spectra reveal fine details in emission and absorption lines, showing how gas temperature and velocity vary with radius. Numerical models reproduce these features by solving equations of magnetohydrodynamics under relativistic conditions. The results confirm that the disk is not a static ring, but a living structure continually stirred by turbulence and threaded with magnetic fields. Through such studies, Cygnus X-1 has become a touchstone for testing ideas about how black holes grow and how they radiate. The disk also serves as a clock marking the passage of time in the black hole's environment. Quasi-periodic oscillations, subtle, repeating modulations in brightness appear in its X-ray light curve. These oscillations likely correspond to vibrations or precessions in the inner disk, caused by frame dragging or resonance effects. By measuring their frequency, scientists can probe conditions close to the event horizon, where matter orbits only a few times before vanishing. Each oscillation is a brief echo of the gravitational engine's rhythm. Despite decades of study, many aspects remain uncertain. The exact mechanism of angular momentum transport, the geometry of the corona, and the details of jet formation continue to challenge models. Yet every new observation refines the understanding of how matter behaves under extreme gravity. In the process, Cygnus X-1 serves as a scale model for the much larger accretion disks found around supermassive black holes and galaxies. The same principles, mass inflow, magnetic turbulence, relativistic rotation, govern systems across a range of scales. At its core, the disk surrounding Cygnus X-1 represents one of the universe's most efficient engines. From gas drawn out of a nearby star, it produces radiation visible across light years. Every photon that reaches Earth from the system originated in a particle's final orbit around a point of no return. The glow we observe is not the black hole itself, but the last light emitted before matter crosses its threshold. Even as the source seems constant, the activity within it never ceases. The disk thickens and thins, brightens and fades, stirred endlessly by forces invisible yet measurable. It is a balance of gravity and motion of order, sustained by turbulence, a perpetual demonstration of how energy is born from the simplest act in the universe, matter falling inward. Closer to the black hole, where gravity exerts its full strength, the physical conditions become extreme beyond analogy. Here the accretion disk narrows and heats to temperatures of tens of millions of degrees, emitting radiation that peaks in X-rays. At these distances, matter no longer behaves as it does elsewhere in the universe. Electrons and ions move at relativistic speeds, magnetic fields twist space into arcs, and time itself slows relative to observers far away. This is the region where the ordinary laws of motion are replaced by the geometry of general relativity. To describe it, scientists use the concept of space-time curvature rather than force. Gas orbiting near the event horizon follows paths determined by this curvature, forming rings whose velocities approach the speed of light. The inner edge of the disk marks the boundary of stable orbits. Within it all, matter inevitably plunges inward. In Cygnus X-1, this radius lies only a few dozen kilometers from the center, yet it determines the system's entire energy output. The processes at work in this inner region are invisible directly, but their signatures appear in the changing patterns of X-rays. Rapid fluctuations in brightness, sometimes occurring hundreds of times per second, reflect the motion of gas in the last few stable orbits before disappearance. These quasi-periodic oscillations serve as traces of the inner disk's structure, offering rare glimpses into the behavior of matter under conditions where gravity bends both space and time. When plotted, they reveal characteristic frequencies that depend on the black hole's mass, and spin, allowing astronomers to measure these parameters with remarkable precision. In Cygnus X-1, the oscillations correspond to orbital periods of only a few milliseconds, meaning that gas circles the black hole hundreds of times in the span of a single human heartbeat. At such distances, radiation pressure, magnetic stress, and relativistic effects interact in complex ways. The energy released by infalling gas heats the surrounding plasma, while the curvature of space-time redirects light, causing photons emitted from the far side of the disk to bend around and reach observers on Earth. This gravitational lensing creates subtle asymmetries in the observed spectrum, with one side of the disk appearing brighter, because its motion is toward the observer. The effect known as Doppler boosting provides additional confirmation of the disk's rotation and orientation. By analyzing these distortions, scientists can reconstruct the geometry of the innermost region even without direct imaging. The light that escapes from near the event horizon also carries information about the black hole's spin. In a non-rotating black hole, the innermost stable orbit lies farther from the center than in a rapidly spinning one. Observations show that the emission from Cygnus X-1 originates very close to the theoretical limit, implying an almost maximal spin. This rapid rotation likely results from the angular momentum of the progenitor star that collapsed to form the black hole preserved during the process of gravitational collapse. A spinning black hole drags space-time around with it, a phenomenon called frame dragging. Near Cygnus X-1, this effect causes the inner disk to precess tilting slightly as it rotates. The resulting modulation in light detectable in the X-ray data gives further evidence of how relativity shapes the environment. Above the disk, the corona acts as a restless halo of charged particles. It is tenuous, yet energetic, its temperature reaching hundreds of billions of degrees. Here electrons collide with photons from the disk, boosting their energy through inverse Compton scattering. The result is a tail of hard X-rays extending to very high energies, sometimes accompanied by brief gamma-ray flashes. The corona's structure is inferred from these emissions. It may form compact magnetic loops, or an extended atmosphere surrounding the black hole. Its activity rises and falls as magnetic fields reconnect, much like solar flares, but on a far greater scale. These reconnection events inject energy into the plasma, altering the system's spectrum within seconds. In addition to light, the inner region of Cygnus X-1 emits streams of matter along its poles, narrow high-speed jets visible in radio wavelengths. Though faint compared with the X-ray emission, these jets reveal another pathway for energy release. Theoretical models suggest that magnetic fields anchored in the disk extract rotational energy from the black hole, launching plasma outward at nearly the speed of light. The jets extend for trillions of kilometers before dispersing into interstellar space, carrying with them information about the processes at the core. They also interact with the surrounding medium, forming weak radio lobes that trace the system's long-term activity. To study these features, astronomers rely on instruments capable of time resolution measured in microseconds and spectral resolution precise enough to distinguish individual atomic transitions. Satellites such as Chandra, XMM, Newton and NuStar have observed Cygnus X-1 across a broad range of energies, capturing subtle changes in brightness and spectral shape. Each observation refines the understanding of what occurs at the threshold of the event horizon. When combined with theoretical simulations, these data create a coherent picture: gas spiraling inward, magnetic turbulence, heating the plasma and radiation, escaping from regions where gravity distorts time and light. Despite the sophistication of these models, direct observation of the event horizon itself remains impossible. The region inside this boundary emits no light. It is defined precisely by that absence. Yet its presence is unmistakable through the behavior of the material outside it. No surface reflection, no periodic signal, and no sudden halt in radiation are seen, only the smooth decline in emission as gas disappears from view. This absence is the ultimate proof of the black hole's nature. If the central object had a solid surface, infalling matter would produce a detectable burst of radiation upon impact. None is observed. The energy simply vanishes, replaced by the steady glow of the accretion disk's outer regions. As matter crosses the event horizon, it carries with it angular momentum and magnetic fields, adding them to the black hole's total. Over millions of years, this process will gradually alter the black hole's mass and spin, shaping its evolution. The energy released along the way propagates through space-influencing regions far beyond the system itself. Radiation from Cygnus X-1 ionizes nearby gas clouds, heating them and changing their chemistry. The faint radio jets stir the interstellar medium-carving cavities that expand over centuries. Even at this distance, the black hole's influence extends far beyond its immediate surroundings. The study of Cygnus X-1's inner disk has also illuminated fundamental physics. It provides a testing ground for general relativity in the strong field regime, where predictions diverge from Newtonian intuition. Measurements of light bending redshift and time delay all align with Einstein's equations to within observational limits. These confirmations are significant because they occur under conditions impossible to replicate elsewhere. The system acts as a natural laboratory, verifying theoretical principles through its own existence. And yet, despite all that is known, the black hole itself remains a mystery of simplicity and depth. It has no surface, no solid structure, only mass, spin and charge. Everything else, radiation, motion, complexity, belongs to the matter around it. Cygnus X-1 demonstrates that the most energetic phenomena in the universe arise not from the black hole itself, but from the struggle of matter as it approaches it. What we see is the final act of falling repeated endlessly as new gas replaces the old, as the system continues its silent cycle of transformation. To study it is to look at the boundary between existence and disappearance, illuminated not by the darkness within but by the light it compels matter to release before surrender. Above the luminous disk and the curved space-time of the inner system lies a region of violent invisible energy known as the corona. This zone, although diffuse, plays a decisive role in shaping the radiation that escapes from Cygnus X-1. It consists of highly energetic electrons suspended in magnetic fields that rise like loops above the disk's surface. The gas here is so hot that its temperature can exceed hundreds of billions of degrees, enough to scatter lower energy photons from the disk into far higher energies. This process, called inverse Compton scattering, transforms soft X-rays into hard X-rays and gamma rays. The corona's brightness changes erratically as magnetic fields twist and reconnect, sometimes forming compact structures close to the black hole, and sometimes extending outward in large arcs. These changes create the complex variability seen in Cygnus X-1's light curve, an irregular flickering signal that never truly repeats. The origin and behavior of this corona are among the most challenging aspects of high-energy astrophysics. It is sustained by the same magnetic fields that stir the disk below it, fields generated by the motion of conducting plasma. When the disk's differential rotation wanes, these fields' tension builds until they snap and reform, releasing bursts of energy that heat electrons to extreme temperatures. The radiation they produce illuminates the surrounding gas, creating fluorescent emission lines in the X-ray spectrum. Among these is the iron K-alpha line, a feature broadened and skewed by the effects of relativity. Its shape tells astronomers how fast the gas is moving and how close it lies to the event horizon. In Cygnus X-1, the line's distortion confirms that much of the emission originates only a few gravitational radii from the center, where the curvature of spacetime is profound. Beyond the corona, the system sends matter and energy even farther into space through narrow jets, aligned roughly with the black hole's spin axis. These jets are composed of plasma accelerated to relativistic speeds, confined and guided by magnetic fields that act like rails. Radio telescopes on Earth detect them as faint elongated features extending billions of kilometers from the core. The jets are not continuous. They flare and fade with changes in the accretion rate switching on during certain spectral states and disappearing in others. The mechanism that launches them is still debated, but most models agree that it involves magnetic extraction of energy from the black hole's rotation. In this way, the same spin that bends space near the event horizon powers streams of matter that pierce the interstellar medium. As the jets move outward, they interact with gas and dust that fill the surrounding region of the Cygnus arm. Though their energy density is small compared with the black hole's radiation, their momentum stirs the interstellar environment, producing shock fronts that heat and compress nearby clouds. Over millions of years, such feedback may influence star formation around them. In this sense, even a stellar mass black hole participates in the broader ecological balance of the galaxy, injecting energy into its surroundings and preventing complete stagnation of the medium. The radiation emerging from the corona and jets varies in a coordinated but not identical rhythm. Observations show that changes in the X-ray output are followed by delayed responses in radio emission, a pattern that traces the propagation of disturbances from the inner disk to the jet. By measuring these delays, scientists can infer the speed of plasma flows and the size of emission zones. In Cygnus X-1, these analyses indicate that material in the jets moves at about half the speed of light. The precision of such timing studies requires instruments capable of registering fluctuations 1,000 times per second, transforming the chaotic flicker of photons into quantitative knowledge about cosmic motion. The corona's intense radiation also influences the disk below it. High-energy photons bombard the surface, heating it, and producing a reflected component in the X-ray spectrum known as the Compton hump. This reflection carries information about the disk's composition and inclination. By fitting models to the observed spectra, astronomers can measure how much of the radiation is reprocessed and how much escapes directly. These measurements, when compared across decades of observation, reveal that the system's geometry remains broadly stable even as its brightness changes. The disk, corona, and jets operate as parts of a single mechanism governed by gravity, magnetism, and rotation. Studies of polarization add another layer of insight. Light scattered in the corona acquires a preferred orientation, and by measuring this polarization, scientists can deduce the spatial arrangement of emitting regions. In 2022, a dedicated X-ray polarimetry satellite confirmed that the electric vectors of Cygnus X-1's X-rays are aligned in a way consistent with emission from a compact flattened corona hovering above the disk. Such results bring the abstract physics of accretion into tangible form, showing that even in deep space, geometry leaves a measurable mark on light. The variability of the system is not purely random. Long observations have uncovered cycles lasting weeks or months, possibly linked to precession of the disk or to changes in the companion star's wind. When the star's outflow intensifies, the accretion rate rises, feeding the disk and brightening the X-rays. When the wind weakens or the geometry shifts, the system dims. These cycles, superimposed on shorter fluctuations, give the light curve a pattern of nested rhythms from milliseconds to months, all generated by interactions between matter and gravity. Despite the violence of these processes, the energy released from Cygnus X-1 does not escape unchecked. Radiation pressure and magnetic forces create feedback loops that limit how much matter the black hole can consume at once. If the inflow becomes too dense, the outward pressure of photons repels additional gas, stabilizing the system. This self-regulation explains why Cygnus X-1, though powerful, remains steady on long timescales. It radiates at a small fraction of its theoretical maximum, a quiet giant rather than a runaway beacon. To human senses, this entire drama unfolds in silence and darkness. No colour, sound or motion betrays it in the visible sky, yet instruments above the atmosphere convert its invisible energy into graphs and spectra that tell a coherent story. A blue supergiant shedding matter, a black hole feeding on that matter, and a network of magnetic fields transforming their interaction into light and motion. Through Cygnus X-1, astronomers have come to understand that the same physical laws governing laboratory plasmas operate here under vastly greater gravity and scale. The corona's turbulence, the jet's acceleration, and the disk's rotation all express universal principles written into the structure of matter itself. The black hole's surroundings thus form a complete ecosystem of energy conversion. Gas flows in radiation escapes, and a small portion of matter is hurled back into space. Nothing remains static. Every region is coupled to every other. The corona brightens, the disk responds, the star's wind shifts, and the whole system settles into a new equilibrium before changing again. It is a perpetual cycle of imbalance, seeking balance of inflow matched by outflow of gravity countered by radiation. Through these mechanisms, Cygnus X-1 endures as a stable yet endlessly dynamic structure, a microcosm of the processes that govern the universe at every scale. In its flickering X-rays and faint radio whispers lies the record of that balance preserved across 6,000 light-years of interstellar space. Cygnus X-1's capacity to launch narrow jets of matter, each extending billions of kilometers into space, demonstrates how black holes can convert gravitational energy into motion. These streams of plasma, traveling at a significant fraction of light speed, emerge from the regions just outside the event horizon. Their formation depends on the alignment of the black hole's spin, the geometry of the accretion disk, and the configuration of the magnetic field lines threading through both. The jets are not steady flows but intermittent outbursts appearing during specific accretion states when the corona expands and magnetic pressure builds to a critical point. Once released, their particles remain confined for long distances before dissipating into the interstellar medium, carrying away angular momentum and energy from the central engine. Radio telescopes detect them as elongated features on either side of the source, sometimes extending several astronomical units. These faint radio signals, combined with the bright X-rays from the disk, confirm that the same system can emit energy across a vast range of wavelengths. The physics governing these jets mirrors that observed around supermassive black holes in galaxies, but on a smaller scale. Magnetic field lines anchored in the rotating disk act as channels for charged particles, while the black hole's spin imparts rotational energy that accelerates the outflow. The process is thought to follow the Blanford-Znaiec mechanism, where magnetic tension extracts energy directly from the black hole's rotation. In Cygnus X-1, this means that the jets are powered not only by accretion, but also by the stored angular momentum of spacetime itself. The result is a system that converts the gravitational collapse of one star into an engine, influencing its surroundings across light years. The interaction between the jets and the interstellar medium produces weak shock fronts visible in radio wavelengths. These shocks compress and heat the gas they encounter, creating filamentary structures that evolve over centuries. Though faint, they mark the boundaries of the black hole's influence. In the dense environment of the Cygnus arm, These disturbances may help trigger the formation of new stars by squeezing clouds of molecular gas. Thus, the energy released near the event horizon eventually contributes to the ongoing renewal of the galaxy. The same pattern occurs on much larger scales in galaxies where jets from supermassive black holes regulate star formation across thousands of light-years. Cygnus X-1 provides a local observable version of that universal process. Because the jets are aligned at a small angle to our line of sight, their apparent brightness is affected by relativistic beaming. Radiation from material moving toward Earth is amplified, while emission from the opposite jet is dimmed. This asymmetry allows astronomers to estimate the jet's velocity and orientation. Measurements indicate speeds of about half the speed of light consistent with other stellar mass black holes in similar systems. The kinetic energy involved is enormous, equivalent to the total output of the Sun over many millennia, yet still only a fraction of the energy released by the accretion disk. Monitoring these jets requires coordinated observations across different wavelengths. Radio arrays such as the Very Long Baseline Interferometry Network trace their shape and motion, while X-ray and optical telescopes monitor changes in the accretion disk that may trigger new ejections. In some cases, bright radio flares follow X-ray dips, suggesting that when the inner disk temporarily collapses, part of its material is expelled outward rather than swallowed. The timing of these events provides insight into how magnetic reconnection and pressure build-up in the disk can lead to sudden release of energy. Even as the jets extend into space, most of the system's power remains confined near the black hole. The radiation field there is so intense that any particle entering it is quickly accelerated and stripped of electrons. The magnetic fields twist into spirals, channeling some material outward while forcing the rest inward. The result is a balance between accretion and ejection. Only a small fraction of matter escapes, while the majority crosses the event horizon, adding mass and angular momentum to the black hole. This feedback regulates the overall brightness of Cygnus X-1, keeping it below the theoretical limit known as the Eddington luminosity, where radiation pressure would exceed gravitational pull and halt accretion entirely. The study of these jets has broader implications for astrophysics. They demonstrate how energy extraction from a rotating black hole is possible, and how magnetized plasma behaves in curved spacetime. The same equations that describe Cygnus X-1 apply to quasars' gamma-ray bursts and microquasars elsewhere in the universe. In this way, a single stellar mass black hole becomes a model for understanding phenomena millions of times larger. Because it is relatively close to Earth, Cygnus X-1 allows detailed repeated observations that would be impossible for distant galaxies. Within the system, the jets contribute to a complex pattern of feedback. As they move through surrounding gas, they produce radio emission that fades gradually over months. This emission carries information about the density of the interstellar environment, the magnetic field strength, and the history of ejections. By comparing old and new outbursts, scientists can reconstruct a timeline of activity stretching over decades. These records reveal that Cygnus X-1 has remained active since its discovery, its energy output remarkably consistent despite continual small-scale variations. The relationship between Jet's disk and corona remains an area of active research. Observations indicate that when the disk cools and the corona expands, conditions become favourable for jet formation. When the disk brightens and heats, the jets fade. This anti-correlation hints at a deeper connection between the two energy channels, one dominated by light, the other by motion. Both originate from the same gravitational well drawing from the same reservoir of matter. The exact balance between them depends on how magnetic fields redistribute angular momentum and energy. Despite their speed and power, the jets of Cygnus X-1 do not escape entirely unaffected by gravity. As they pass near the black hole, their paths curve slightly, creating helical structures seen in detailed radio maps. Farther out, they interact with ambient gas slowing and diffusing into faint plumes that mark the outer limits of the system's reach. These features are faint reminders of the processes taking place deep within where light bends and time dilates. The study of these outflows has also refined distance measurements. By tracking the apparent motion of knots within the jets, astronomers can triangulate the system's true scale. The agreement between these dynamical distances and parallax measurements strengthens the reliability of both techniques. In this way, Cygnus X-1 has contributed not only to understanding black holes, but also to calibrating methods used across astronomy. Viewed in its entirety, the system is a network of flows, stellar wind feeding the disk feeding the black hole, and black hole feeding the jets. Each component exchanges energy with the next, and all are bound together by gravity's geometry. The jets represent the final stage of this cycle, carrying away the excess energy that cannot be radiated as light. Over millions of years, they sculpt the interstellar medium, leaving behind traces that persist long after individual outbursts fade. Through them, the invisible heart of Cygnus X-1 communicates with the galaxy, beyond sending a steady message of motion and transformation that continues long after the matter that produced it has vanished into the darkness from which no light returns. The study of Cygnus X-1's spin has become one of the most revealing aspects of modern black hole physics. A black hole's spin, described as its angular momentum, defines how space and time behave in its vicinity. Rotation drags the fabric of space-time around the object, an effect predicted by Einstein's theory of general relativity and confirmed only through indirect observation. For Cygnus X-1 measurements suggest a spin rate near the theoretical maximum. This means the black hole completes hundreds of rotations per second, a motion so fast that the innermost stable orbit of its accretion disk lies very close to the event horizon. Determining this spin required precise modelling of the X-ray spectrum, particularly the thermal emission from the disk and the shape of the broadened iron line. When gas orbits near such an intense gravitational field, the photons it emits experience both gravitational redshift and Doppler effect, stretching and skewing the spectral lines. By comparing observed data to predictions from relativistic models, scientists deduced that Cygnus X-1's dimensionless spin parameter must be nearly 1, signifying an almost maximally rotating black hole. This rapid spin reveals much about the object's origin and history. If the black hole had formed from a supernova explosion that ejected most of the progenitor's outer layers, its spin might have been lower. The measured value implies instead that the collapse was relatively quiet and direct, preserving much of the angular momentum from the original massive star. The event that created Cygnus X-1 likely involved the core of a very heavy star imploding under its own gravity, without a bright outward blast forming a black hole in an instant. Its companion, HDE 222688, survived the event, retaining its orbit and continuing to feed the remnant through its stellar wind. This survival is remarkable, as such gravitational events often disrupt binary systems entirely. Cygnus X-1 therefore provides rare evidence that black holes can form without destroying their stellar partners. The influence of the black hole's spin extends beyond the disk. Rotation determines how magnetic fields behave near the event horizon, influencing the structure of the corona and the power of the jets. The faster the spin, the greater the energy available to drive outflows through magneto-hydrodynamic processes. Observations show that Cygnus X-1's jets, though modest in size, are consistent with this high spin configuration. In essence, the black hole acts like a dynamo converting rotational energy into electromagnetic power that threads through the disk and accelerates particles outward. The gravitational field around such a rapidly spinning object exhibits phenomena unique to relativity. One of these is frame dragging, where space itself is pulled around the black hole's rotation axis. Any object near the event horizon must rotate in the same direction, not because of physical contact, but because space-time itself is twisting. In Cygnus X-1, this effect causes the inner part of the accretion disk to align gradually with the black hole's equatorial plane, a process known as the Bardeen-Petersen effect. The alignment changes the disk's tilt over time, influencing how its light appears to observers on Earth. Such subtle adjustments are visible in long-term monitoring of the system's X-ray polarization and spectral shape, providing direct evidence of frame dragging in action. Measurements of time delays between different energy bands also confirm the black hole's rapid rotation. High-energy photons from the corona respond to variations in the soft X-rays from the disk, with minute lags reflecting the finite time it takes for light to travel across the inner region. These lags, often only a few milliseconds, can be modelled to infer the size of the emitting zones. In Cygnus X-1, the results show that the corona and disk are tightly coupled within just a few gravitational radii, consistent with the presence of a highly spinning black hole. Another consequence of rapid spin is its effect on the efficiency of accretion. For a non-rotating black hole, only about 6% of infalling matter's rest mass is converted into energy before it disappears. For a maximally spinning one, the efficiency rises to more than 40%. This means that Cygnus X-1, even while consuming only a modest amount of material, radiates with enormous power. The conversion of matter to light here approaches the theoretical limit of energy generation in the universe. Every photon emitted from the disk represents energy drawn from both the infalling gas and the rotational momentum of spacetime itself. To quantify these processes, astronomers combine X-ray spectroscopy, radio imaging, and optical monitoring into unified models. Decades of data show that the black hole's spin has remained nearly constant since its discovery, suggesting that the current accretion rate is too low to alter its angular momentum significantly over observable timescales. The stability of its spin contrasts with the variability of its radiation, demonstrating that while surface conditions change rapidly, the underlying geometry endures. The presence of such a high-spin black hole also influences predictions for gravitational waves. If Cygnus X-1 eventually evolves into a double black hole system when its companion star collapses, the pair's merger would produce a distinct gravitational wave signature, shaped by their spins and masses. Models based on Cygnus X-1's parameters suggest that such an event would be detectable across vast distances, providing insight into how black hole binaries evolve and coalesce. For now, this remains a future possibility, but it links the system to the broader study of cosmic collisions observed by instruments like LIGO and Virgo. Spin measurements also provide a test for theories of black hole growth. Because accretion can either spin up or spin down a black hole depending on direction, and alignment tracking spin over time reveals the history of mass transfer. In Cygnus X-1, the alignment between the black hole's spin axis and the orbital plane suggests that the accreted matter has flowed in the same direction for millions of years, steadily reinforcing the existing rotation. The consistency of this orientation implies a long-term equilibrium between the two components, a balance achieved through continuous gravitational coupling. The study of spin has forced astronomers to confront the abstract nature of black holes as objects defined by only a few parameters. Everything that once composed the original star, its element structure and radiation, has vanished, replaced by three measurable quantities: mass spin and electric charge. In practice, charge is negligible, leaving mass and spin as the defining features. Cygnus X-1 shows that even with such simplicity, the resulting phenomena are extraordinarily rich. The interplay between rotation and gravity generates the corona, drives the jets, and shapes the light we observe. Each photon escaping from the vicinity of the event horizon carries the imprint of these two numbers. As observation and theory advance, Cygnus X-1 continues to serve as a benchmark. Its near-maximal spin challenges models of stellar collapse, tests the limits of relativity, and bridges the behavior of stellar mass black holes with that of the supermassive ones at galactic centers. Through it, scientists have learned that rotation is not a secondary detail, but a fundamental driver of cosmic structure. It defines how energy escapes, how magnetic fields evolve, and how matter behaves near the most extreme boundaries of physics. In the silent sky of Cygnus, the black hole turns endlessly invisible, yet shaping everything around it, its spin transforming gravity into light, its motion preserved as the enduring memory of the star from which it was born. Over time, the two members of the Cygnus X-1 system continue to evolve, bound together in an intricate gravitational relationship that is both stable and slowly changing. The blue supergiant HDE 222668, though immense and brilliant, is losing mass each year through its powerful stellar wind, and that mass is partly drawn toward the black hole's pull. The transfer is not constant. It varies with the density of the wind, the star's temperature, and even the subtle pulsations of its outer layers. Every change in the companion star alters the black hole's environment, causing small shifts in brightness and spectral energy. On human timescales, these changes are minor, but over millions of years they will reshape the system entirely. The star's gradual depletion will widen the orbit, and as its internal fuel diminishes, it will expand and cool, evolving into a supergiant of different character before collapsing under its own gravity. When that happens, Cygnus X-1 may become a pair of black holes, a system that will orbit quietly for eons before merging in a burst of gravitational waves invisible to light but detectable across galaxies. Today, the system is near a delicate equilibrium. The orbital period of roughly 5.5 days remains constant within fractions of a second. The mass ratio between the two bodies sets a center of gravity located inside the massive star itself, meaning that both orbit an invisible point not centered on either. This configuration causes the star to appear slightly distorted when viewed from Earth, its surface stretched along the axis toward the black hole. The side facing the black hole glows faintly brighter due to heating by X-ray radiation, while the opposite hemisphere shines more purely in blue-white starlight. Over each orbit, small changes in brightness trace this pattern, providing a natural clock that has kept perfect rhythm for decades of observation. Despite the constancy of this rhythm, subtle long-term trends emerge in the data. The orbital separation appears to be increasing slowly, likely due to mass loss from the system, as stellar wind escapes into interstellar space. This process conserves angular momentum, but reduces the gravitational binding energy, allowing the two bodies to drift slightly apart. The effect is minute, measurable only over thousands of years, but it illustrates the delicate balance between inflow-outflow and orbital motion. These long-term changes also hint at the eventual fate of the system, which will depend on how quickly the massive star exhausts its nuclear fuel. The internal structure of HDE T26868 is already unstable. Its core fuses helium into heavier elements, building layers like the shells of an onion. As it evolves, these shells contract and heat until fusion reaches elements that cannot release further energy. At that stage, gravity will overcome pressure, leading to collapse. If enough mass remains, the core will become a black hole, if slightly less a neutron star. Either outcome will transform Cygnus X-1 from a mixed pair into a double compact system. Such systems are rare but have been detected through gravitational wave observatories which record the ripples in spacetime produced when two black holes merge. Cygnus X-1 offers a preview of the conditions that may lead to such an event far in the future. For now, the energy output remains steady. The black hole continues to accrete matter at a modest rate, converting it into light with extraordinary efficiency. The blue supergiant continues to shine with steady brilliance, maintaining an outward pressure that counters further collapse. Their balance produces one of the most stable X-ray sources in the galaxy. Decades of monitoring have shown that despite fluctuations lasting seconds or hours, the system's overall power remains nearly constant across years. This constancy makes Cygnus X-1 a cornerstone of high-energy astrophysics, a reference point against which other X-ray binaries are measured. Advances in observation technology have made it possible to study the system with unprecedented precision. Optical interferometry can resolve slight variations in the star's shape, while radio interferometers trace the minute wobble of the system's position on the sky. These data yield direct distance measurements accurate to a few percent, confirming that Cygnus X-1 lies about 6,070 light-years away. This distance anchors the calibration of X-ray luminosities for many other systems, extending its influence beyond its own neighborhood. In a sense, Cygnus X-1 serves as both a subject of study and a cosmic measuring stick. The system's evolutionary path also informs understanding of how black holes are distributed through the galaxy. The existence of a stellar mass black hole in a binary with such a massive companion suggests that similar systems must have formed elsewhere. Surveys using space telescopes have identified dozens of candidates, each showing the same combination of an optical star and a compact invisible partner emitting X-rays. Many of these systems resemble Cygnus X-1 in mass and brightness, implying that its formation process is not unique. It represents a common stage in the life cycle of massive stars, a reminder that the most luminous objects in the sky can end their lives as sources of pure gravity. Another area of research focuses on the system's magnetic environment. Observations show that magnetic fields pervade not only the accretion disk, but also the space between the two stars. These fields influence how the stellar wind flows, shaping it into spirals and filaments. Magnetic reconnection events near the black hole may explain sudden bursts of hard X-rays, while longer-term field alignments could govern the orientation of the jets. Understanding these processes requires modeling the interaction between plasma and curved spacetime, a field still developing but heavily guided by systems like Cygnus X-1. The constant radiation from the system also affects nearby interstellar clouds. Ultraviolet light from the supergiant and X-rays from the accretion disk ionize hydrogen gas, creating faint glowing regions that can be detected with sensitive instruments. Over long timescales, this ionization may influence the chemical composition of the local interstellar medium, enriching it with ionized elements and heating it enough to alter future star formation. Thus, the system's reach extends far beyond its immediate orbit, affecting the structure of its galactic environment. As both components age, their mutual influence deepens. The black hole gradually gains mass, though only by a small fraction, while the star steadily loses it. Eventually, as the star nears the end of its life, the balance may reverse. If the mass ratio changes enough, the orbit could shrink instead of widen, drawing the two objects closer. The result might be an era of intense accretion, when the star's outer layers are stripped and swallowed rapidly, producing a surge of radiation brighter than anything seen before in the system's history. Such a phase could last only a few thousand years, a blink in cosmic time but would mark the transition from stellar life to compact binary. The fate of Cygnus X-1 illustrates the continuity between stellar evolution and cosmic recycling. The black hole, once the core of a massive star, now receives material from another star that will one day join it in collapse. The elements forged in both will disperse into space through winds and radiation to be gathered again in new stars. What appears as a static system is in fact a step in an endless sequence of formation, decay and renewal. For now it remains balanced between these extremes, emitting its constant light while drifting slowly toward transformation. In the quiet night sky, the point of Cygnus X-1 seems motionless, but within it forces of unimaginable scale continue their steady exchange, linking the life of one star to the gravity of another, and carrying the memory of that union across thousands of light years through an invisible beam of X-rays. Since the discovery of Cygnus X-1, the instruments used to study it have evolved in ways that mirror the growth of astronomy itself. The first detections came from rockets that spent only minutes above the atmosphere, registering crude counts of X-ray photons without precise positions. Today, observatories in orbit can measure the energy timing and polarization of those same photons with extraordinary accuracy. Each generation of technology has added new dimensions to what can be known about this system, turning a point of mystery into a well-charted cosmic laboratory. The early satellites of the 1960s and 70s established its existence and general behavior. Missions in the 1980s mapped its spectral states and variability, and those of the 21st century have resolved its fine structure, even measuring how light scatters within its environment. Through these advances, Cygnus X-1 has become one of the most observed objects beyond the solar system, its data spanning more than half a century of continuous study. The timeline of observation begins with the Uhuru satellite, which first revealed the changing intensity of its X-rays with reliable precision. Later missions, such as Ariel 5 Hiao and Exosat, tracked its cycles of high and low emission, identifying the two spectral states that define its behavior. With the launch of the Compton Gamma Ray Observatory in the 1990s, scientists detected even higher energy radiation, confirming that the system produced not only X-rays, but also hard gamma rays indicating the presence of extremely energetic electrons. Each technological improvement brought finer understanding, yet the core features remained unchanged: a massive star, a compact object, and a shared field of gravity that converts mass into light. When the Chandra and XMM Newton observatories began operation at the turn of the millennium, they delivered a new level of clarity. High-resolution spectroscopy showed individual emission and absorption lines, revealing the complex structure of the stellar wind as it flowed toward the black hole. These spectra displayed signatures of multiple ionization states of iron, silicon, and oxygen, each corresponding to a specific temperature and distance from the source. From them, astronomers reconstructed a three-dimensional picture of the wind's motion, temperature, and density, showing how radiation pressure and magnetic fields sculpt it into arcs and filaments. The data also revealed how the X-ray emission from the black hole ionizes the surrounding gas, creating a feedback system that shapes the environment on both large and small scales. Around the same time, advances in radio astronomy provided complementary views of the system. Very long baseline interferometry linking antennas across continents allowed the measurement of Cygnus X-1's position with millisecond accuracy. This precision made it possible to detect the tiny wobble caused by its orbit, leading to the first direct parallax distance measurement for a stellar mass black hole. The result, about 6,070 light-years, confirmed earlier estimates and established a foundation for all subsequent energy calculations. With that distance, known scientists could determine absolute luminosity mass and accretion efficiency without relying on uncertain assumptions. Observation across multiple wavelengths also showed that the system's behavior is interconnected. When the X-ray flux changes, the radio emission from the jets follows suit after a short delay, linking processes near the black hole with those in the distant outflow. Optical and ultraviolet light from the companion star respond in turn to the changing illumination, displaying spectral shifts that echo the black hole's rhythm. This network of responses spanning the electromagnetic spectrum transforms the binary into a natural laboratory for testing how energy propagates across vastly different regions of space. The instruments themselves record not just brightness, but also timing with extraordinary precision. Modern detectors can measure fluctuations in Cygnus X-1's X-ray emission on microsecond scales, enabling studies of oscillations corresponding to the innermost orbits of the disk. These observations allow direct comparison with predictions from general relativity. The measured frequencies match the motion expected for matter, circling a black hole of about 15 solar masses, providing one of the most direct confirmations of Einstein's theory in the strong field regime. Over decades of monitoring, these frequencies have remained consistent, showing that the system's mass and spin have not changed appreciably, a cosmic stability that contrasts with the turbulence of its individual photons. In addition to space-based telescopes, ground-based observatories contribute to the picture by measuring how Cygnus X-1 interacts with its environment. Infrared surveys reveal the heated dust illuminated by the system's radiation, while optical interferometers capture the shape of the companion star's elongated atmosphere. Radio arrays detect the weak glow of the jets as they collide with interstellar gas. Each observation adds another layer of understanding, and when combined they form a continuous chain of evidence stretching from the early era of X-ray astronomy to the present day. The development of theoretical models has kept pace with these observational advances. Early interpretations of the data use simplified assumptions about spherical symmetry and constant wind flow. Modern simulations incorporate magnetohydrodynamics, radiation transfer, and general relativity, reproducing the observed light curves and spectra in remarkable detail. Supercomputer calculations trace the path of individual gas streams as they spiral inward, heating and ionizing before merging with the disk. They show how small changes in magnetic field orientation can switch the system from one spectral state to another, explaining the transitions seen by satellites decades apart. In these models, Cygnus X-1 becomes not just an observation, but a process, a dynamic interaction that can be recreated and tested mathematically. Long-term monitoring has also revealed slower cycles that may relate to precession of the disk or to variations in the stellar wind. These cycles unfold over months or years, modulating the system's brightness and polarization. By studying them, astronomers gain insight into how angular momentum is redistributed within the disk, and how large-scale structures evolve under the combined influence of gravity and radiation. The persistence of these patterns across generations of instruments attests to the system's stability, a cosmic rhythm maintained despite the constant motion of matter and energy. The legacy of observation extends beyond science alone. Cygnus X-1 was the first object to transform the black hole from a theoretical concept into an empirical reality, bridging the gap between mathematics and measurable fact. Its discovery in the early years of the space age marked the beginning of high-energy astrophysics, inspiring the development of new instruments and methods that have since explored the entire sky. Every modern X-ray or gamma-ray telescope traces its lineage to those early attempts to understand this source. Even now, data from Cygnus X-1 continue to calibrate instruments and test algorithms used for distant galaxies and quasars. As technology improves, the possibility of observing the system in new ways grows. Future missions plan to measure X-ray polarization across a wider range of energies, map the disk's rotation through time-resolved spectroscopy, and detect subtle changes in gravitational field using next-generation interferometers. Each new measurement promises to refine the understanding of how matter behaves in the universe's most extreme conditions. In the quiet of deep space, Cygnus X-1 remains constant, its light flickering with the same pattern it has displayed for decades. To observers on Earth, this steadiness is a reminder of continuity. The same photons that first revealed its presence still arrive, carrying information about events occurring 6,000 light-years away. The instruments that detect them have changed beyond recognition, but the source itself endures, as if to demonstrate that while human knowledge advances through invention, the universe continues its work in silence. Cygnus X-1 has watched the rise of satellites, the refinement of theory, and the birth of gravitational astronomy. Its presence has turned one small corner of the constellation Cygnus into one of the best-studied places in the Milky Way, a point of light that has taught generations of scientists how to listen to the invisible. Even after decades of continuous study, Cygnus X-1 remains an object of uncertainty. The precision of its measured mass spin and distance leaves little doubt about its nature. As a black hole, yet details of its environment still resist complete explanation. The rate at which matter transfers from the companion star varies unpredictably, driven by fluctuations in the star's wind and the complex geometry of the flow. Some days the system emits powerful X-ray flares. At other times it settles into relative calm. The causes of these transitions between high soft and low hard states, between radio loud and radio quiet phases, are not fully understood. The best models suggest that they result from changes in the temperature and thickness of the accretion disk and corona, but the precise mechanism linking one state to another remains elusive. Even with advanced satellites measuring X-rays in microsecond intervals, the system's behavior defies perfect prediction. This unpredictability has become its defining signature, a sign that the processes near a black hole are inherently chaotic and nonlinear. Astronomers refer to this behavior as variability, and in Cygnus X-1 it occurs across all timescales from milliseconds to years. On short scales, it reflects turbulence and magnetic reconnection in the inner disk. On longer scales, it traces cycles in the stellar wind and orbital geometry. By studying these fluctuations, scientists attempt to understand how accretion transforms gravitational energy into radiation. The light curve of Cygnus X-1, when plotted over long periods, resembles a restless heartbeat rising and falling in irregular patterns. Statistical analyses reveal that its variations follow a pattern known as red noise, where power decreases with increasing frequency. This property is common in systems governed by complex feedback loops, where small disturbances amplify and propagate through the whole structure. Thus, what appears to be randomness may in fact be the visible signature of self-organizing dynamics. One of the ongoing mysteries concerns the exact mass of the black hole. Early estimates placed it around 15 times the mass of the Sun, but improved distance measurements have revised this figure upward, possibly as high as 21. This difference, though small in human terms, significantly affects calculations of spin, luminosity, and evolution. If the mass is indeed larger, the black hole must have formed from an exceptionally massive progenitor, one that collapsed directly without a supernova explosion. Such an event would represent a type of stellar death still rarely observed, where the star simply implodes into darkness. Confirming this scenario requires precise modelling of the system's orbit and distance tasks that new instruments like the Gaia satellite are refining year by year. Another uncertainty lies in the alignment of the black hole's spin with the orbital plane. If the spin axis is tilted relative to the orbit, the disk may precess producing periodic changes in the observed X-ray and radio emission. Some data suggest that such precession occurs over cycles of months, while others indicate alignment so close that no measurable effect exists. Determining which is correct matters because it reveals whether the black hole inherited its spin from the progenitor star or gained it through accretion. If aligned, the system has remained stable since birth. If tilted, its geometry has evolved under the slow torque of gravity. Each possibility offers clues to the formation and growth of black holes across the galaxy. The chemical composition of the companion star also presents puzzles. Spectroscopic studies show anomalies in its surface, abundances of carbon, nitrogen, and oxygen signatures of material that has undergone nuclear fusion deep inside a star. This suggests that the outer layers of HDE 226868 have been mixed with processed material from its core, perhaps through rotation or tidal distortion. It may also indicate past episodes of mass transfer, when the now black hole was still a massive star exchanging material with its companion before its collapse. In that earlier phase, the two stars would have shared a common envelope spiraling closer as friction removed angular momentum. The current configuration with its tight orbit and ongoing transfer is the remnant of that earlier interaction. Understanding such histories helps explain how close binaries survive the violent events that create compact objects. Modern instruments continue to find subtle variations that hint at deeper complexity. Polarimetric data show that the orientation of X-ray polarization changes slightly over time, possibly reflecting shifts in the corona's structure. Radio mapping detects faint knots in the jets that move outward and fade, tracing bursts of ejection correlated with specific X-ray states. Even gravitational wave detectors, though not yet sensitive enough to register signals from such a wide binary, could one day capture tremors from instabilities in its orbit or from interactions in its accretion flow. Each advance expands the ways in which Cygnus X-1 can be measured, transforming it from a point of light into a system whose every component leaves a quantifiable mark on space-time. The persistence of unknowns has not diminished the system's importance. Instead, it has become a benchmark for the limits of understanding. Scientists use it to test not only models of accretion, but also the performance of instruments. Its steady brightness allows telescopes to calibrate detectors, ensuring that data from distant sources remain reliable. In this sense, Cygnus X-1 is both a subject and a tool of observation, a cosmic standard candle for X-ray astronomy, even though its nature is anything but simple. Over the decades, public perception of black holes has also evolved alongside the science. When Cygnus X-1 was first proposed as such an object, the idea was controversial. Some physicists doubted that nature could produce singularities or that a real star could collapse so completely. The confirmation of its mass and invisible nature helped shift black holes from theory to observation. Since then, the term has entered common language symbolizing mystery and power. Yet the true character of Cygnus X-1 is quieter than myth suggests. It does not devour stars in sudden flashes or send destructive beams across space. Its feeding is steady, almost gentle, limited by physical laws that ensure equilibrium. The energy it emits is immense but constant, its influence strong but contained. What makes it remarkable is not violence, but endurance. In the larger context of galactic evolution, Cygnus X-1 represents one of countless binaries where massive stars end their lives in collapse. most will never be observed as clearly hidden behind dust or too distant to resolve. But by studying this single nearby example, astronomers can infer the behavior of thousands. Each pattern of X-ray variability, each spectral transition, serves as a model for systems far beyond the reach of direct observation. In that way, the uncertainties surrounding Cygnus X-1 are not failures of knowledge, but signs of richness, the inevitable complexity of reality at the edge of physical law. Despite its enigmas, some aspects of the system appear immutable. The orbit remains stable. The average luminosity has not changed significantly since its discovery. The companion star continues to supply matter in a steady stream. Its consistency over half a century suggests that even in the most extreme environments, long-term balance is possible. Gravity radiation and magnetism, though competing, find equilibrium through feedback and adjustment. The result is a cosmic machine that runs without rest, converting mass to energy with quiet efficiency. In the end, the uncertainties surrounding Cygnus X-1 are part of its lasting appeal. It embodies both the success and the limits of human investigation, a system so well measured that its smallest fluctuations are known, yet so governed by fundamental physics that it resists complete prediction. The more closely it is studied, the more it reveals the subtle interplay of order and chaos that defines the universe. What remains unseen beyond its horizon continues to symbolize the boundary between knowledge and mystery, a place where even light must surrender, but where understanding continues to expand. Cygnus X-1 persists not as a riddle to be solved, but as a companion to inquiry itself, unchanging, enigmatic, and endlessly instructive. Among all the known stellar mass black holes, Cygnus X-1 remains the most deeply studied its steady light and proximity, allowing it to become a cornerstone of modern astrophysics. It stands as both a relic of stellar death and a window into the dynamics of extreme gravity. Over half a century of observation has revealed much about its composition, yet what continues to make it remarkable is how it links local processes to universal laws. Through Cygnus X-1, astronomers have traced how massive stars live and die, how energy is released from the fabric of space-time, and how the smallest regions of matter can shape structures that stretch for light years. In the Milky Way, where hundreds of billions of stars reside, Cygnus X-1 occupies only one faint point within the Northern Cross, yet it has altered how the galaxy itself is understood. The black hole and its companion exist within a larger neighborhood of massive stars, clusters, and nebulae. The Cygnus arm where they lie is rich with star-forming regions such as the Cygnus OB3 and OB2 associations. Within these clusters, stellar winds and supernova remnants create bubbles of hot gas that drift through space, merging and colliding in slow motion. The presence of a system like Cygnus X-1 among them shows one outcome of this environment: stars so massive that their lives end not with dispersal, but with collapse. The radiation from its accretion disk contributes to the broader X-ray glow of the region, faintly detectable even against the galaxy's background. On large scales, such sources help heat the interstellar medium, influencing the balance between gas and dust that determines where new stars will form. Thus, a single black hole system participates in shaping the galactic ecology, connecting microscopic plasma processes to the birthplaces of future stars. In terms of physical parameters, Cygnus X-1 defines the archetype of a high-mass X-ray binary. It has a stellar companion of about 40 solar masses, an orbital period of roughly 5.5 days, and a black hole of 15 to 21 solar masses. Its X-ray luminosity varies between 100,000 and several 100,000 times that of the Sun. These numbers, derived from decades of measurement, form the foundation upon which theories of accretion and compact objects rest. When astronomers analyze newly discovered systems, they compare them to Cygnus X-1 as a reference, just as earlier generations compared stars to the Sun. The system's consistency gives it the role of a cosmic standard, a stable pattern against which variations elsewhere can be understood. Yet its constancy hides ongoing change. The blue supergiant is losing mass each year, and the black hole gains a minute fraction of it. Over millions of years, this exchange will subtly alter the system's orbit and energy output. Eventually, as the star nears the end of its nuclear fuel, it will expand and cool, possibly transferring mass more rapidly before collapsing itself. If it leaves behind another black hole, the two will orbit each other in silence, their mutual gravity causing them to spiral together until they merge. The energy of that merger will ripple through space-time as gravitational waves, a phenomenon already detected from other binary systems, but one that would, in Cygnus X-1's case, link a familiar object to the larger cosmic network of such events. Even if this happens tens of millions of years in the future, it will mark the final chapter in a process that began with the birth of two stars in a single cloud of gas. For the present era, Cygnus X-1 continues to serve as a bridge between observation and theory. Data from missions such as Chandra XMM Newton New Star and the Imaging X-ray Polarimetry Explorer are combined to reconstruct its environment with unprecedented detail. Measurements of its X-ray polarization confirm that light near the black hole is bent and scattered in ways consistent with general relativity. Time-resolved spectroscopy allows scientists to follow individual fluctuations, tracking how brightness changes propagate through the disk and corona. Radio interferometry captures the faint jets, their motion mapped over years, to reveal consistent alignment with the black hole's spin axis. Together, these techniques provide the most complete portrait of a black hole ever assembled, showing not just its energy output but the fine structure of its surroundings. The continuing interest in Cygnus X-1 also reflects the questions it leaves open. The system challenges understanding of stellar evolution because its components appear older than the surrounding population of stars. This suggests that they may have originated elsewhere in the galaxy and drifted into their current location. Calculations of their velocity through space support this idea the system moves more slowly than the fast-moving stars ejected by supernova explosions, implying that its black hole formed quietly through direct collapse. If so, it provides a living example of how black holes can emerge without the violent shockwaves that once seemed necessary. This quiet origin may be common, meaning that many black holes across the galaxy formed in silence, invisible except for the X-rays of their later feeding. The system's long observational history has also taught astronomers how to interpret data from more distant sources. The behavior of its accretion disk, its spectral states, timing patterns, and polarization matches that of much larger systems around supermassive black holes in active galaxies. The same physics applies across a range of scales: gravitational energy converted to radiation by spiraling gas magnetic fields, controlling the flow and jets carrying away excess angular momentum. Cygnus X-1 thus acts as a microcosm of the active universe, compressing processes that shape galaxies into a single nearby laboratory. For many researchers, the appeal of Cygnus X-1 lies in its combination of clarity and mystery. It can be measured with extraordinary precision, yet what it represents, a hole in space where time stops, remains beyond complete visualization. Observations confirm that no light escapes that matter, vanishes once past the horizon, but the internal reality of the black hole remains unknowable. Theories describe singularities and quantum effect, yet none can penetrate the final boundary. Cygnus X-1 stands as a reminder that even in a universe governed by measurable law, some regions will always lie beyond direct knowledge. The energy we detect is not from the black hole itself, but from matter in its final moments of existence transformed into light by gravity. Every photon that reaches Earth from this system marks the end of a journey that began with the disintegration of atoms near the event horizon. Viewed across the decade, Cygnus X-1's importance extends far beyond its own sky position. It has shaped the methods of astronomy-driven technological progress and guided theoretical physics. It turned black holes from mathematical curiosities into physical realities and continues to refine how those realities are understood. From early rocket flights to modern space observatories, it has remained a constant target, its flickering X-rays serving as both subject and benchmark. Even now it surprises with subtle variations that reveal new aspects of the forces at play. In the quiet distance of 6,000 light-years, the binary continues its unending exchange. A star shedding its mass, a black hole receiving it, and a surrounding field glowing with the energy of that transaction. Around them, the Milky Way turns its spiral arms, drifting through time. The photons leaving Cygnus X-1 tonight will cross that space for 6 millennia before arriving at Earth, where new generations of instruments will still be watching. For those who study it, the system embodies the link between change and permanence, between the transient lives of stars and the enduring shape of physical law. It is both a remnant of what has been and a model of what will come, demonstrating that in the universe, death and creation are one continuous motion. Cygnus X-1 endures as the first and still the most eloquent black hole ever found, a silent engine at the edge of perception, turning gravity into light and time into memory across the endless dark of the Milky Way.